Hello everyone, my name is Dimas Bahtera Eskayudha from Hiroshima University, Japan. Today I would like to talk about a proposed seaplane float in water entry problem and landing in wave using particle-based method. The first content is introduction. Indonesia is developing the first seaplane, as you can see in the middle picture, that has some function like passenger transportation, logistic transportation, surveilling, medical evacuation, and also for rescue. And as we know, this is the Indonesian archipelago region that has a lot of islands there. So uh, to fulfill the needs for of the flexible transportation mode in Indonesia, seaplane can fulfill the gap, and that's why Indonesia developed the first seaplane that equipped by pair of float which has function to withstand load and of the plane and maintain the airplane on the water surface stably. And the advantage point of the seaplane is land for runway is not necessary, faster than ship, and floating airport or seaport solve site difficulties and also environmental issues. So this is the crucial part because it replaces the landing gear to be float. That's why the mature study of this part of this float is needed, and the technical aspect is crucial to be assessed in this study. In this study, we focus on the landing phase. As we know, the landing is one of the critical moments which need to be assessed. The failure of the landing process in discipline can cause structure damages, instability, and in the worst case, capsizing. And in this study, the proposed float design are inspired from Shamswar et al. 2021, and this is the general shape of the floater or seaplane float. And the purpose of this study is to determine the water impact between the proposed design of the float and the water surface when in the landing phase through the water entry problem and landing in calm water and waves by using particle-based method. The next content is about numerical methodology. Okay, this is the overview of smooth particle hydrodynamic or SPH. And as we know, in the computational fluid dynamics, the formulation is based on the continuity equation and also equation of motion, like this formula. And in this SPH, the discretization by particles is expressed as the physical quantity that smooth by kernel function like this. So the seaplane floats and also the free surface water will be defined as the particles. And by employing all the formulation here in the SPH, we employ the dual physics that introduced by Crispo et al. 2050, and with some features such as based on SPH methods, method, this software, this open source software, and acceleration of flow analysis by CPU and GPU is possible, and fluid structure coupling analysis, and also it based on the C++ language, which have high degree of freedom in program change. And the program structure in the dual physics is divided into three kind of the process. The first one is pre-processing, main processing, and also post-processing. Okay, next, this is the application to seaplane float, and this is the water entry problem. And this is the 1/10 scale model of the float in 2D because we do the simulation in water entry problem in 2D. And this is uh, the general dimension here is 150 millimeters. The height is 142 millimeters, and the dead rise angle is the 20 degrees generally. And this is the wedge model that have a flat bottom surface compared with the model A and model B that has a flare, double flare here. And specifically in the model B, I add the rails as an additional part to reduce the impact pressure here. And this is the computational domain. So the water depth is 0.7 meters, the width is 0.84 meters, and the vertical velocity of the model will be divided into three variation. The first one is 0.69 meter per second, 1.28 meter per second, and 1.6 meter per second, and it equal to 345 meter per second in actual scale model. And P1, P2, P3 here, it is show the monitoring point during the water entry problem. So we analyze the pressure distribution and also velocity field to calculate the potential energy and also the kinetic energy. And also the second simulation is like this is the simulation in landing in calm water and also waves. So the scenario is similar. So the seaplane float here, and this is the trajectory, and there is three steps. The first one is landing, hydroplaning, and also takeoff, and this is the water surface. And the scenario is like this. I divided the velocity into two kind of velocity. The first one is horizontal velocity, and the second one is vertical velocity. The horizontal velocity has same value, and the vertical velocity has different value. It depends on the operation here. The first one is 0.31, and in the hydroplaning is 0 meter per second, and in takeoff is 0.31 meter per second. And the wave period in the simulation of landing in waves, the wave period is 1.68 second, wavelength is 3.89 meter, and wave height is 0.1, and the pitch angle is 9.79 degrees based on the Q et al. Work, which is considered as optimum angle when teaching to reduce the impact. And this is the bird eye 3D view and monitoring area, the red rectangular here. Before we conducted the simulation for the Seaplane float, we reproduced the experimental data using dual physics based on Iafrati et al. And this experiment used flat plate as representative of aircraft when teaching. In the simulation, we simulate in 10 degrees and 4 degrees as shown here. The fluid structure interaction between flat bed and also water surface with splashing and droplet can be found here. You can see as the result, the maximum pressure is comparable and the steady pressure is slightly have different value. But in overall, uh, the result has a good agreement to do the simulation with water entry and also landing in calm water and waves. Now the result and discussion. Okay, this is the result and the discussion. And first one is about the water and the problem. And we can see that the high pressure region is strongly exceeded near the bottom surface of every proposed design of the seaplane float. As we can see, the red one is the highest and the blue one is the lowest. And this is the object in velocity 0.96 meter per second, and the splashing and drop with droplet can be found here under the fluid structure interaction between the model and the water surface. And this is the pressure time series in 0.96 meter per second, and this is the comparison result, and we can see that uh, the model B has a minimum pressure in the first impact here, as you can see here in the middle of the model. It is because the rail component here that 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 be added in this model. And yeah, this is the details of every single velocity in every position P1, P2, and P3. The and this we can see the difference here. The pressure value is increased gradually, in every in the increasing of the velocity. And we can see the point here that the model in P1 and P2, the model B, the first impact is minimum, this one and this one. And after the steady pressure is occur in the simulation, the model B has slightly lower pressure, but in the P3, in the position 3, the um, overall the model A has the lowest pressure here, as you can see, the red one, and the wedge has a highest pressure here. And then this is the velocity field, and this is the definition formula of the potential energy and the kinetic energy. So the potential and kinetic energy are calculated using vertical position and velocity at all particles, which is expressed as fluid energy caused by interaction between model and the water surface. And we can see the result that all of the potential energy and also kinetic energy, the result is comparable, and it assumes that it's because uh, the potential energy and the kinetic energy are uh, are calculated in the computational domain range. So all particles are included here. So that's why the disparity of the value among the model is very small. Okay, next, this is the landing in calm water and landing in waves. It is the animation view, and the simulation is this simulation specification is distant particle is 0.02, and the total particle in calm water is uh, 80 18 millions, and the total particle in the uh, wave landing waves is 6 millions. And the graph is, you can see like this in the calm water. uh, yeah, this we can see the first impact here after the seaplane is landing, and then the peak pressure of the calm water uh, is in the second impact here. So the value is over 300 kilopascal, and after that the steady pressure is occur here until the seaplane take off. And then in the second picture, second video, this is the landing in waves, and we can see the difference here. And in this part, the seaplane hits the wave 3 times because uh, we we can see the periodic wave here, and the seaplane is hit the wave 3 times in shorter time. So that's why the maximum pressure of the wave, sorry, the maximum pressure of the seaplane in the floater is lower than the waves. So it less than 150 kilopascal, and it is occur in the third waves here. And the last one is conclusion this study. So we developed the computational model based on the particle-based method by using dual physics of Seaplane float model to reduce the impact pressure and splashing with droplets. In the water entry problem, model B with the additional rail part has slightly minimum value compared to wedge and the model A in P1 and P2. But in the P3, the model A has a lowest pressure and the wedge excited the highest pressure overall. The tendency of the fluid energy consists of the potential and kinetic energy are comparable in the domain of the particles. Generally, the developed model can be investigate the characteristic of the proposed Seaplane float and reproduce the accurate and realistic result. Further investigation of the landing wave process in wider range domain and finer particles should be needed, and the model validation should be required with experiment as future work. Thank you for listening.